Researchers solve a scientific mystery about evaporation. Evaporation can explain why water levels drop in a full swimming pool, but it also plays an important role in industrial processes ranging from cooling electronics to power generation. Much of the global electricity supply is generated by steam plants, which are driven by evaporation. But determining when and how quickly a liquid will convert to a vapor has been stymied by questions about how, and how much, the temperature changes at the point where the liquid meets the vapor, a concept known as temperature discontinuity. Those questions have made it more difficult to create more efficient processes using evaporation, but now researchers from the University of Houston have reported answers to what happens at that interface, addressing 20 years of conflicting findings. The work was reported in the Journal of Physical Chemistry c. The temperature discontinuity was first reported in 1999 by Canadian researchers G. Fang and C. A. Ward, who noted that they were unable to explain the phenomenon through classical mechanics. The new work solves that mystery. Hadi Ghassemi, Cullen Associate Professor of Mechanical Engineering at UR, said the new understanding eliminates the bottleneck that has complicated predictions and simulations of processes involving evaporation. We demonstrated the physics of what happens within the space of a few molecules at the interface and accurately developed a theory on the evaporation rate, Ghassemi said. That allowed us to explain all of the conflicting findings that have been reported in the last 20 years and solve this mystery. In addition to Ghassemi, co-authors for the paper included first author Param Jafari, a PhD student at UR, and Amit Amritkar, a research assistant professor at UR. The researchers first approached the question in the lab, but Ghassemi said they were unable to get the needed spatial resolution for a definitive answer. They used a computational approach in order to find the properties of liquid and vapor within the length of a few molecules. The explanation, developed using the direct simulation Monte Carlo method, will allow scientists to more accurately simulate the performance of all systems based on the theory of evaporation. With this understanding, we can more accurately develop simulations of performance and efficiency, as well as design and predict the behavior of advanced systems, Ghassemi said. That would have applications for energy, electronics, photonics and other fields. As just one example of the importance of evaporation, Ghassemi noted that 80% of electric power globally is generated through steam plants, which work based on evaporation phenomena.